So delighted to be joined today by Melodie Yashar, who is a space architect, which is a job I didn't even know there was. It's amazing to speak to you today. Thank you so much for joining us on the Polymath World.
Thank you. It's a pleasure.
So I heard your TED talk a few years ago about building habitats on Mars before people would even arrive. And it was one of the most innovative things I'd heard for a long time. And I thought all my students need to hear this. This is absolutely amazing. So could you tell us, what is a space architect and how does someone become one?
Yeah, space architecture is kind of an emerging discipline in aerospace engineering, not a well-recognized one, but essentially it's someone who focuses on the design and conception of habitats supporting human life beyond Earth, either in orbit or on surface habitats on the Moon and Mars. So the talk that I gave at TED and a lot of my work in the last 5-6 years has been focused on surface architectures and using in-situ materials to actually create those habitats that can sustain a permanent human presence on both the Moon and Mars.
Yeah, and how did this happen for you? Were you was young Melody just looking up at the moon, thinking one day I'm going to build houses on that?
It was actually, I always knew that I wanted to work at the intersection of design and technology. Space always represented the pinnacle of those things for me, and also kind of represented what we can accomplish in terms of humanity's collective achievement and pioneering innovations in both science and exploration are really they are really represented through space exploration. So, it happened very naturally, actually. There were a number of NASA competitions around 2014, 2015 that asked the general public to conceive of a 3D printed habitat. Multiple companies, groups, designers, and also technology, I would say organizations were founded as a result of this competition and this solicitation to think about technologies for 3D printing on the surface of Mars. And I was part of one of such groups, and it really spun off into an entire research trajectory and career that no one could have anticipated. Multiple of the leaders within the technology space for terrestrial additive manufacturing got their start and incubated their technologies as a result of competing in that competition. So it really fostered a wave of ideas and also concepts for space architecture and habitation around that time.
That's brilliant. And we love where these things intersect in STEM here on Polymath World. And you got two master's degrees, if I'm right. You got one on the sort of the arts and creative design side and one on the robotics side. So I suppose this is sort of a natural fusion of your interests and ambitions.
Yes, that's right. I have a master's in architecture and then another that focuses on human-computer interaction, but particularly the relationship of astronauts. I focused in my work on the relationship of astronauts with autonomous systems. So how, in a remote spaceflight environment, astronauts and crew members are actually going to be able to solve problems and complete work, execute procedures without the support of ground control or mission control on Earth. These are big challenges when we think about long duration space flight, when we think about transit journeys to Mars, and construction is just one of those challenges. So it's been a wonderful confluence of themes, problems, and ideas that have really spawned my research and inspired me ever since.
Yes, and this is one of the reasons why I just thought we have to talk to you, because if we don't get this right, we'll forever be stuck just living in low Earth orbit. And as wonderful as that is, this is one of the biggest problems to solve. And it seems to have been the focus of your work for your whole career. I mean, you were at the NASA Ames Research Centre for a
Yes.
while, weren't you? What were you doing there?
So I was in the Human Systems Integration Division at NASA Ames within the Human Computer Interaction Lab, which is a lab that essentially creates technologies supporting astronauts in, yeah, I would say in simulation environments is one such thing. I was part of the SPIFFy group, which provided a crew scheduling interface for all of the analog missions that NASA currently operates. And so it introduces a way for the astronauts to manage their schedule, introduce a little bit of flexibility and rearrange their schedule as needed, and also establishes a communication platform within a time-delayed environment. These are all critical needs that we need to study and that are ongoing in research and human behavior and performance at NASA. And also it addresses critical gaps. Like we really don't know how crews are going to perform, how they're going to behave, what the parameters for a successful mission to Mars are actually going to be. And so we need these simulation environments, we need these analog environments to do that research and resolve those gaps.
Yes, I'm on the board of the Mars Society here in the UK, and we always have analog astronauts going to caves for a couple of months or
Yeah.
up the mountains. I suppose the most famous one is the Russian guys who spent a year in a car park in an analog environment. So, but people don't. The general public doesn't know much about analog astronauts. So you were sort of supporting essentially these practice missions to troubleshoot and find out what could go wrong. Is that right?
Correct. We were providing scheduling software to these analog missions, as well as to other, I guess you could say, programs at NASA. And that was our main contribution on the technology side. I should say that when I left NASA Ames, I left to start a department at icon. Around that time, there was a solicitation, a request for information from 3D printing companies and former contestants of the 3D printed habitat challenge. I received that solicitation and basically partnered up with icon to submit a proposal to build the crew health and performance exploration analog, which is currently the longest running NASA analog mission at Johnson Space Center. It's a 1 year long analog mission. So we were able to design and then print that analog habitat. And so far, they've completed their first mission. It's certainly not the longest analog in the world, but it's the longest one that NASA has completed to date.
Yeah, there's a lot there you've said that I'm really excited to get into. Could you start by telling us what Icon is?
Yeah, so Icon is a company I used to be a part of. I was the vice president of building design and performance. They are a large-scale additive manufacturing provider based in Austin, Texas, delivering solutions for terrestrial additive manufacturing, particularly to address what they believe is a global housing crisis, so introducing rapid growth within the residential sector, but also in delivering advanced additive manufacturing concepts for space. So in particular, they're focusing on lunar construction and delivering various kinds of infrastructure using additive manufacturing technologies on the moon.
Right. That's just sounds totally incredible. And here's where we find design and technology for space really having a massive impact on life on Earth, because your programs of building habitats could really play out tremendously in terms of helping these housing crises here on Earth. Let's get into the problem though. 3D printing is really disruptive for space technology. And we were talking to Laura Gonzalez last week, who is the CEO of Radian Systems in Spain, and they're 3D printing rocket engines
Yeah.
in space. Tim Peake, one of our own British astronauts for the European Space Agency, was recently speaking about bioink and 3D printing on the International Space Station and the potentials of that for human health. But you're 3D printing entire habitats for the moon and Mars, as well as landing pads, and you've actually done this on Earth at NASA Johnson Space Center, haven't you? So
Yes.
yeah, can you break down how this can be done and what the incredible potential of it is?
Yes, yes. So right now, the work that's happening terrestrially, like here on Earth, with 𝐂onnect at least, is using cementitious extrusion. So this is a mortar-based cement material that has been specifically engineered to be 3D printed. In space, we're not actually planning to use cementitious materials on the surface of the moon. We're looking at directed energy deposition processes and processes that are similar to like a powder bed fusion technology that you have in 3D printing on Earth, but only using the local and indigenous regolith, which is the soil on the surface of the moon. And so developed technologies there to actually demonstrate that we can print small coupons, which are small material samples, in vacuum and using hardware that would be built and ready to go on the moon. And that entire experimental setup of the robotic end effector, as well as the laser, as well as how this entire system will operate in vacuum, has already been tested at NASA Marshall Space Flight Center. So they're ready and waiting to become flight manifest so that we can demonstrate this technology and print and verify a structural sample on the south pole of the moon within the next several years.
Yeah, so you're essentially making space bricks from the material on the land.
That's right.
Now, I got to ask about the transport because landing stuff on the moon is hard. Landing stuff on Mars is much harder. How are you going to transport the equipment? Is that one of the easier aspects of the challenge or one of the harder ones?
No, I would say nothing is easy, that's for sure. In an initial technology demonstration mission on the surface of the moon, we had been planning to be basically to be manifest aboard one of the 𝐂onnect missions, the commercial lunar payload systems. So we would have a robotic arm that would be a payload aboard the 𝐂onnect mission, would be able to scoop, sieve, and process the regolith directly from the lander itself. And in future missions go off lander, so have a mobility platform that could actually create larger structures and introduce different kinds of structural samples that can also be tested and verified. And just as you mentioned, we're not only interested in creating these small samples, we actually want to create permanent infrastructure. So things like roadways, berms, civil engineering elements that are going to be essential for a lunar base, and eventually building upwards, building vertically, and thinking about habitats and other kinds of unpressurized radiation shields.
Let's I'd like to ask you specifically about the robots here that can do
Yeah.
this. You mentioned Wally in your TED talk, and I had to smile
Yes.
because my daughters and I love Wally, and Wally is absolutely my favorite Disney film of all time. And if not exactly like Wally, when you were describing it and showing the animations, it sort of did remind me of the other robots in the Wally film. So can you just tell us a bit more about what these robots are and how they'll work and how they'll do the 3D printing?
Yeah, of course. Um, the simplest, most reliable, and durable design is what I believe is going to be the most successful in a remote and extreme environment such as Mars. These robots will need to operate autonomously. They'll need to have decision-making capabilities to know where to go and what to do. Um, else, and we can't imagine that these are going to be like large construction scale robotics, not at first. That is just going to be too difficult to deploy, too difficult and to manage, and the energy constraints of such a system will just be tremendous. So we have to imagine small scale excuse me, small scale robots that can operate independently, that are extremely durable, just like Wally, and those are going to be the most successful systems in the remote and extreme environment that we're going to have to operate in.
Well, that sounds like an immense challenge. They'll have to operate independently. Essentially, this is largely because of the time scale, the time gap, the lag between Earth and Mars, which is considerable. These robots are essentially going to have to know what to do and make the decisions themselves, aren't they?
Yes, especially when we're talking about construction activities, which are so time sensitive. And when we're talking about material deposition and certain elements being interfaced and integrated within an overall construction sequence, it's a matter of seconds by which certain tasks and certain operations happen. And so when you're in a time delayed environment, you have perhaps like a 22-minute delay in communications between knowing what's happening on Mars in construction versus what's communicated back on Earth. It'll be too late to actually intervene or solve a problem that that the robots might encounter. And so we want to imbue them with as much decision-making capability, as much autonomy as possible to resolve problems or stop work, even better, so that we can intervene and address at the critical moments when it's most necessary.
Can I ask you about the different terrain? Because while it's a real positive that you can make the bricks and the equipment you need from what you have readily available on the moon and Mars, the terrain is not easy. So what sort of challenge does that pose for building with these robots, but also how can it be overcome?
There certainly are going to have to be leveling, compacting, and site preparation activities that need to happen before any kind of construction begins. So we want to think about how to create foundation systems for habitats, for example. That is more often than not going to require a flat and level terrain that needs to be cleared of any, like large boulders, medium-sized boulders. And so we also need construction robots for excavation, compaction, leveling, in addition to construction tasks. So it's an entire slew of tasks and operations that we need to consider even before construction begins. Um, in the grand scheme of in-situ resource utilization, regolith is being imagined to be used for a wide variety of extraction possibilities. And so there's a lot of vested interest from multiple companies to actually deliver excavation and I would say regolith processing and handling technologies to move the material in bulk from one area to another and use it for extraction purposes to extract oxygen or water and other metals and other precious metals, things like that. So there's a lot of interest in just general earth moving on the surface of the moon and Mars, and that's absolutely going to be one of the capabilities that's needed before construction.
And when we think about building landing pads and human habitats and greenhouses and things like this, I know a lot of people are going to be thinking, how on earth can you make it safe for humans before they arrive? And in particular, I want to ask you about how you can make them airtight, but also the problem of radiation. I mean, my own area of research is DNA repair, and one of the first concerns is, well, how can you build habitats that can effectively shield and protect people from the immense radiation on the moon, especially Mars?
Right. So in my opinion, one of the main reasons why we're interested in regolith construction is to produce radiation shields that can protect the crew against galactic cosmic rays, solar particle events, and all the hazards of deep space radiation. Of course, yeah, like secondary to that, we want them to live in a comfortable environment where they can deliver on their mission activities, do research, whether it be geological in nature, biological in nature, and make sure that they are in a comfortable and safe and durable place to live. But first and foremost, we need to be sure that they're protected against the hazards of deep space radiation. And regolith is a fantastic material for that. The more mass you actually introduce to attenuate that radiation, the better the astronauts will be in terms of health and safety. other materials that are very good are materials that are hydrogen rich. So high density polyethylene has been considered as a good radiation shield. Water has been considered as a good radiation shield. And it's a true problem that we have to think about both for Mars transit as well as for living and operating on the surface of the planet.
Yeah, a lot of the theoretical early ideas were around astronauts living in caves on the moon and Mars. But if you can take that material because of its strength in shielding from radiation and have them not live in a cave but live in a proper domain, that's going to be a lot more enjoyable, I'm sure, for people. Um, but what about the airtight factor? How can you really make sure it's completely sealed? For people who've seen the Matt Damon Martian movie, everyone remembers the bit where the hab blows up and he has to sort of get that plastic sheeting to make it
Mm.
shielded. And I know I was a lot of people worried like it's not going to stay intact. He's obviously going to implode when it pops. So how can these habitats keep all the danger of air escape out?
Yeah, it's I think that in a Mars context, the first reason or rationale why we would not want a regolith-based structures or shells to be the primary pressurization layer or bladder or restraint layer is because it contains toxic perchlorates, which the astronauts should not interface with. Secondary to that, I mean, regolith is materially porous. Depending on what your deposition technology is, it's questionable whether you can actually create that airtight barrier that we need to contain pressure on the inside. And so there are multiple technologies and I guess you could say ways that we're considering how to create that pressurized interior. I personally believe that multiple redundant systems are necessary to actually create that enclosure. So considering a membrane like an inflatable is one such way. Introducing some kind of spray liner that is a higher technology readiness level than printed regolith would be another, to introduce an airtight barrier. And there's just a lot more testing that needs to happen to really advance the technology readiness level of 3D printed habitats and other regolith constructed habitats, and make sure that they're safe and airtight for future crews.
Now, in terms of other hazards of the surface of the moon and Mars, anyone who's seen any of the Apollo missions, but especially Apollo 17, knows they were absolutely caked in lunar dust by the end of their EVAs, that seems to be quite a problem. And on Mars, obviously, you have dust storms which can cover all your equipment in the sort of the red sandy stuff, but also some of these storms on Mars are quite electrical storms. So both of those present quite a lot of hazards for it. How can you overcome them with 3D printing habitats? And is it a problem?
You know, so dust mitigation is going to be a problem no matter what we're doing, what operations we have, because EVA is like an essential part of exploration, extravehicular activity. So the astronauts are going to be exiting whatever habitat they're in, whether it's a transit habitat like a lander or something like the Apollo lunar module, or whether it's an in situ constructed habitat. They're going to be leaving that environment, going out, exploring, getting regolith all over themselves, and then coming back into the hab. So we want to be sure that the regolith stays outside the hab is the first and foremost consideration. And then beyond that, like whatever measures we can take to mitigate the risk of dust introducing complications when it comes to like its tribology with mechanical equipment and other elements that we're going to have on the surface. It's a huge area of investigation and one that we have to consider for habitats as well, most certainly. I think it's a bigger issue for hardware that's just located on the surface of the moon and Mars. than it is for, the interior space of habitats, but almost certainly whether we have an airlock or some kind of vestibule to contain all of that dust, we need to come up with some kind of solution to mitigate the risk of that regolith coming inside the hab.
Yeah, certainly. Um, Now, as I understand it, if you're going to Mars, you kind of got two options. You can go for a month, or you can stay there for 2.5 years. Um, can we build with what we have, with what you've already done? Do you think we can build habitats on Mars that could endure for 2.5 years and beyond?
Oh, I think that, the reason why we're so interested in construction technologies is we want to introduce habitation and shelter that can last for decades into the future. It's not about creating a simple shack or a structure that can only stand in a matter of years. We're invested in permanent infrastructure. Like permanent landing pads, permanent roadways, and civil type of structures that can meet the requirements of multiple stakeholders and actors on the surface of both the moon and Mars, and be there for decades and decades into the future. So it's really important not only that we have durable construction technology to execute this work, but also that we're building the right things, because you don't have a chance in the same way that you do in terrestrial construction to go back, renovate. At least it's not a very it's an inexpensive option, let's say. Like in-space construction is such that we want to get it right the first time. And so that permanent infrastructure is what we're aiming towards, that will hopefully last decades and centuries into the future.
Yeah, I think this is amazing, and if you're doing it in orbit or on the surface, it is going to be a lot cheaper than just doing it all on Earth and then launching it straight up. So, give me your most hopeful and ambitious and excited um, play out of events. So, how soon could this be done? And in your mind, what would it look like over the next 2 years? What would need to be done in terms of a succession of launches to have everything there ready for when people go to Mars?
Mm. I think that we're going to see multiple types and classes of space architecture emerge on the surface of Mars in conjunction with 3D printing and additive manufacturing. So we're going to see multiple types of landing systems, which will from different companies. I really believe that it should be a diverse and robust ecosystem that we're creating to actually get to the moon and also to Mars. So we'll see multiple types of landers. We'll see different types of hard shell environments where crews can live for about a year. So we're thinking about like cylindrical modules, spherical modules, and we'll also see inflatable and deployable modules, very similar to Bigelow's current edition on the ISS. And we'll see these various types of space habitats emerge, link up. It's very important that we think about how they can connect and utilize similar resources, water, oxygen, etc. And then eventually, we'll also see additively manufactured habitats that are either created prior to those crews being there or created simultaneously to them. So it's extremely important that whatever robotic construction apparatus that we create, it's not only able to operate autonomously separate from the crews being there, but also that they can interact with human systems, that they are safe and durable enough to actually become counterparts with humans in construction. This is extremely important for repair and maintenance over the long term on the surface of Mars, and not something that we typically think about when we're engineering space robotics. Space robotics are typically things that do not need to interface with human beings, but a huge portion of my research is devoted to thinking about how we can create interactive paradigms for construction, repair, and maintenance so that these are systems that we can utilize for decades into the future. I am hopeful that there will be small demonstrations of additively manufactured structures on both the moon and the Mars within this decade. And that's separate from any paradigm to actually have a permanent human presence on the surface of those planets. The technology is ready. I believe that there is adequate research to support the delivery of those robotics to the surfaces of both planets, and I'm very hopeful that we're going to see those demonstrations in the next couple of years.
And this isn't going to be dependent on Starship or something like that. This could be launched with currently available rockets that have already flown payloads to Mars, right?
Yes, and the wonderful thing about this concept of just sending a single robot, a single additive manufacturing robot to the surface of the moon or Mars is that you just need that one system to deliver a wide range of infrastructure. That's really the sustainable key to this technology, is that instead of having to rely on Starship's fairing, right, and send all of that infrastructure over, large-scale HABs, different construction materials for your roadways and other structures, you just need to send one robotic apparatus, one platform, and that's about it. So I don't see it being dependent on Starship, at least not in the early days. I think that there's going to be other habitat paradigms that are considered that will rely on Starship and that fairing to deploy in the future, both in orbit and on the surface of the moon and Mars. But the wonderful thing about additive manufacturing is you just need to send the robot and it will do the rest using the local and indigenous materials.
Yeah, that's wonderful, and it's so tremendously disruptive. And whenever we're talking to students about Mars, a big concern that always comes up is you've got this long trip, and when you land, if they're expected to suddenly do a lot of construction when they're weak, they've been out of Earth's gravity for a long time, and yes, they've been trying to exercise and keep fit, but they're going to land and immediately be required to do a lot of construction. They're not going to be in the shape for it. So if you can have everything built, or even most of it built before humans arrive, well, that changes so much. It really does, doesn't it?
Yes, absolutely.
Yeah.
I don't think it's reasonable for did I lose you?
No, I'm here.
Oh, you're here. Okay, good. I don't think it's reasonable for astronauts to do any kind of construction activity with our current EVA suits. The dexterity just isn't there. We can't imagine that contractor crews, in the same way that we imagine them operating here on Earth, will be able to operate in the environment, remote and extreme environment of space. And so, from my perspective, construction is something that needs to happen robotically. Even if we're not considering additive manufacturing, it's just too dangerous, too complex, and very challenging to have crews doing that. I mean, if you look at the ISS and the pace at which repairs aboard the ISS happen, my goodness, it will be decades before we can even consider a single-story structure being constructed by crews in EVA suits in a microgravity environment. It is too risky and extremely dangerous.
Yes, I mean, even in the Polaris Dawn mission, at the end of last year, when they were using the new SpaceX suits, they still looked quite, there's a lot of mobility tests and it looked very clunky. And I think the flat earthers loved it because they just thought it was puppets on strings rather than actual people trying to move. And I was like, no, they're just trying the new suit. But let's talk about the immense benefits on Earth of the research you're doing, because yes, it's incredibly technologically amazing what you're doing for space, but it will have real implications for life on Earth. Could you tell us a bit more about that?
Of course. Additive manufacturing is a disruptive technology we've already mentioned that is changing the way that construction happens here on Earth terrestrially. It is capable of introducing rapid growth and tremendous volume and production and scale when it comes to delivering housing of a certain size, type, and scale. And because of that, is able to introduce faster, more efficiently built construction at a lower cost than traditional builds. So, the idea here is to use and leverage robotic construction for the greater good of humanity, and actually introduce that efficiency, that rapid speed, and the capacity to build large volumes of structures to actually support, what we believe is a global housing crisis. We simply can't keep up with the demand for housing, at least not in the United States, and worldwide, the costs of construction are just tremendous. And so the way that we've tried to leverage this technology is by a means of introducing a solution to that gap in the housing crisis itself, and introduce housing in areas where labor might be at a shortage, or where materials are not easily accessible, like materials like lumber or concrete. And so this introduces a way of building in remote and extreme environments here on Earth. I mean, they don't have to be extreme, frankly, but just using robotics in a new and innovative way that we maybe had not considered before.
I'd love to, for all the young budding Melodie Yashars out there who would be listening, people who want to get into this field, what would you advise them in terms of study and career path for people who want to get into space architecture?
I would say follow your passion is the number one thing. Get involved with people, researchers, folks in the industry who are doing projects that you admire and that you really relate to and that you want to get involved in. And then people always ask, how can I get involved in space architecture? And the truth is you just do it. You just get started. You think about, what are the needs for a Mars mission? What are the needs for a lunar mission? And don't hold anything back. Everything, from a certain perspective, everything is a problem in space flight. And in my opinion, we need as many voices at the table to address these critical technology and research gaps. Because there's going to be a lot of work to do, frankly, to get there.
Yeah, and at the last conference of the British Interplanetary Society here in London back in November, at least half of the talks were on some aspect of space architecture. So it does seem to be growing and booming. I wanted to ask if there's anyone in particular who inspired you when you were younger.
Well, there's a ton of people. My goodness. I would say that if I can call one out, there were loads of physicists that I admired as a young person, but also many architects as well. I'm fortunate to have been inspired by people in the arts and people in the sciences. And so I would say, never be afraid to look outside of your own discipline for inspiration. That's another thing, is that I've found that repeatedly being confined to one discipline has never resolved or inspired me or introduced the most innovative or disruptive ideas. Really looking cross-disciplinary in other areas has been one of the most inspiring things to me, and continues to be inspiring to me today. So I try to collaborate as much as possible with folks who are focusing on radiation shielding, with folks who are focusing on computational systems for multi-agent systems and swarms and that type of thing. So I would say the most important thing is never to feel confined to your own discipline. When you're looking for inspiration, feel free to look elsewhere.
That's great advice. For people looking for something in particular to get their teeth stuck into, what do you think is the biggest remaining challenge, or can you highlight some of the biggest challenges that we'll need solving for us to truly be an interplanetary species?
Transportation is the biggest one. There are some key players in industry, I believe, that are really leading the way in that regards. But thinking about how we can leverage crewed systems in orbit, whether it be low Earth orbit or in cislunar space, I think this is a really critical question that we're going to have to continually revisit in the next decade. So, what are crews going to do? How can we actually sustain their presence there? And how can they operate in a semi-autonomously operational environment such as the Lunar Gateway? And we'll see what happens to Gateway in the next several years. But these are some really, really critical questions. How do you sustain a crew aboard a semi-autonomous vehicle such as Gateway and cislunar orbit? And then how do you sustain a crew aboard a short mission to the surface of the moon, such as 2 weeks, and then 1 month, and then 1 year?
Just out of interest, do you have any ambitions to be an astronaut yourself? Did you ever think about going to space? Is that something you want to do?
I would love to go to the surface of the moon. I really would. I'm more of a pragmatist when it comes to Mars, and so the transportation opportunity is available, and once it becomes more clear exactly how we're going to sustain and protect crews in that 9-month journey to Mars, at that point I would consider it, but I'm not fully convinced just yet. There are just too many risks and too many things that I haven't wrapped my head around to be able to say, yes, I will absolutely go to Mars tomorrow.
Well, we'll have to talk to somebody about that and see if they can tell us how that problem will get solved. Where can people find out more about you and find out more about your work if they're interested?
Yeah, I have a website. It's www.melodieyashar.com. I'm working on a couple of new projects that I'm excited to announce in the coming months, a new venture focused on in-space construction. And yeah, you can take a look at my website, connect with me on LinkedIn. I'm happy to connect with anyone on any questions or any interest that you might have in this area.
Well, we'll put links to those and to your TED Talk in the description for this. Melodie Yashar, it's been a real pleasure. Thank you so much.
Thank you.
Thank you so much for watching. Don't forget to like and subscribe, and stay tuned for more amazing conversations with incredible researchers who are changing the world we live in and working on the frontiers of driving humanity forwards. For more information, you can check out my Instagram at polymath_Sam or my website at www.sam-mckee.co.uk.